Okay, so let's proceed to part 5, the final interpretation here. We have the equation 4 is equivalent to the Legendre differential equation here. Since the derivative of 1 minus x squared and y double prime is equal to this. So the derivative of y double prime, and we have the given 1 minus x squared, then plus derivative of 1 minus x squared equal to 2xy, 2x. Derivative of y prime is, we have the product of y prime and the derivative of 1 minus x squared. So that is equal to 2x y prime of x. Thus, the identity proves the yn of x satisfies the Legendre equations. Okay, determine the constant c sub n here. Standard normalization is p of 1 is equal to 1. So evaluated at x equal to 1 here. So near x equal to 1, and we have the factor x squared minus 1. So that's equal to the factor of x squared minus 1 is x minus 1 and x plus 1. So we have x minus 1 raised to the n times x plus 1 raised to the n. So since x squared minus 1 here is raised to the n. So taking the n derivative and evaluating at x equal to 1. So we have the right side here is equal to n factorial times 2 to the n. So the n of 1 is equal to c sub n n factorials times 2 to the n times equal to 1. Hence, c sub n is equal to 1 over 2 to the n factorial. So this is what we are going to prove here, or we are going to find the value of c sub n in terms of n factorial and n. So derived identity, let's start with this. We proceed using Leibniz rule for higher order derivatives and analyze the behavior of the function at x equal to 1. So we have to first factor this x squared minus 1 raised to the n factoring. Then we let u of x equal to x minus 1 raised to the n and v of x equal to x plus 1 raised to the n. Now we are going to apply the Leibniz rule here. So this is the Leibniz rule. So we have the combination of n taken k at the time. So the kth derivative of u of x equal to x minus 1 raised to the n. So the kth derivative of u is equal to n factorial over n minus k factorial times x minus 1 raised to the n minus k. So here k is less than or equal to n. So we have the proof here. So step-by-step derivation, power rule. To see where this comes from, we apply the power rule. The derivative of x to the n is equal to nx to the n minus 1 repeatedly. So we apply the power rule here. So the original function is u of x equal to x minus 1 raised to the n. So we have the first derivative here, n times x minus 1 raised to the n minus 1. So the second derivative is n times n minus 1 times x minus 1 raised to the n minus 2. The third derivative here is n times n minus 1 times n minus 2 times x minus 1 raised to the n minus 3. So we have to generalize these factorials. So the sequence of numbers n times n minus 1, n minus 2 continues until we have taken n derivatives here. So this following factorial can be written compactly using standard factorials. So we know that n times n minus 1, that n minus k plus 1 is equal to n factorial over n minus k factorial. So plugging this coefficient and the remaining exponent back together, we get the general formula here. Okay. So why the constant k is less than or equal to n? So if we try to take more derivatives, then the degree of polynomial k is less than n. So the term n minus k would involve factorial of negative numbers, which is undefined in the basic calculus here. So basically, if you differentiate x squared 3 times, you get 0. once the power of x minus 1 reaches 0, the next derivative here makes the whole term vanish. So we have the rule in the Legendre derivatives. This specific formula explains why most terms in the Leibniz expansions vanish when evaluated at x equal to 1. So if k is less than n, the exponent here n minus k is at least 1. So therefore, 1 minus 1 raised to the n minus k equal to 0, causing the entire term to become 0 here. So we have here x here is x approaches to here. So n here is greater than k. So this becomes 0 by using the limit. Then if k equal to 1, the term is n minus n equal to 0. So since 1 minus 1 raised to the 0 is equal to 1, the term survive as the constant n factorial over 0 factorial is equal to n factorial. So we have here 0 to 0 approaches 0 as shown below for n equal to k here. So we have the limit of n raised to the n as n approaches 0. So this becomes 1. Now for n minus k is greater than equal to 2, greater than 0. So we have the limit here. For example, n approaches 0. So we have 2 here. So this becomes 0. So we have the plot here for n to the n as n approaches 0 here. So this is equal to 1. So that's the reason why it is equal to 1. So 1 minus 1 raised to 0 equal to 1. Now it is evidently shown by the plot here that n to the n from 0 to 1. So as from 0 to 1 here, so n equals to 0 here. So 0 to the 0 is equal to 1. So to derive the formula for the n minus k, is derivative of the functions v of x equal to x plus 1 raised to the n. We apply the power rule for differentiation repeatedly. So step 1, we have to first identify the patterns of derivatives. So first look at the few derivatives of v of x equal to x plus 1 raised to the n. So we have the first derivative here. So the first derivative is n times x plus 1 raised to the n minus 1. The second derivative here is n times n minus 1. So x plus 1 raised to the n minus 2. The third derivative here is n times n minus 1, n minus 2 times n minus 2 times x plus 1 raised to the n minus 3. So establish the general formula here. By induction, the nth derivative of v of x can be written as v of m derivative of v of x. So n times n minus 1 times n minus 2 and n minus m plus 1 times x plus 1 raised to the n minus m. So we can represent the term in the brackets more clearly using the factorial. So the m derivative of v is equal to n factorial over n minus m factorial times x plus 1 raised to the n minus 1. So substitute for the n minus squared derivative here. The formula you are looking for is basically as per the n minus k m derivative. To find this, we simply replace the variable m in our general formula with n minus k. So m here is equal to n minus k. So calculate the n minus m. So this is n, and n minus k here is equal to m. So we have the cancellation of n here. So n minus n equal to 0. So this simply becomes k factorial. So calculate that the new exponents now. So n minus m, n minus k is equal to m here. So this simply becomes k. So we have the final result here. So plugging this simplified terms back into the general equations. Here's the formula seen in your notes. So the n minus k derivative of x is equal to n factorial over k factorial. So multiply by x plus 1 raised to the k. So this result is crucial component in the Leibniz rule application for Legendre polynomials, as it allows us to evaluate the derivative at x equal to 1 very easily by turning x plus 1 raised to the k into 2 to the k. So x here is equal to 1, so 1 plus 1 equal to 2, 2 raised to the k. So the n minus k derivative of v of x is equal to x plus 1 to the n is the n minus k derivative is equal to n factorial over k factorial. So x plus 1 raised to the k. So k here is less than or equal to n. So substitute in the Leibniz rule. Leibniz has some. So we have here by using the substitution here. To evaluate that x equal to 1 here. So x minus 1 raised to the n minus k. So this is equal to 0. Now we have already said that for k is less than n. So this becomes 0 here, since n minus k is greater than 1. So only the terms with k equal to n survive, because x minus 1 raised to the n minus k is equal to x minus 1 equal to 0 equal to 1 when k equal to n. So it is geometrically proven by this graph. So we have a plot here, n to the n. As n approaches 0 here, so this becomes 1 here. So that's the only the k equal to n term contributes here. So we have the evaluation of this at x equal to 1. So n combination of n taken n at a time is equal to 1 here. So this is 1. So n factorial divided by the 0 factorial is equal to n factorial here. So this is already equal to 1 here. Then n factorial over n factorial is equal to 1. Then multiplied by the x plus 1 raised to the n. So this one. Now evaluating this at x equal to 1 here. So x here is equal to 1. So 1 plus 1 equal to 2. So this becomes n factorial times 2 to the n. So we have the final result here. All other terms vanish due to the factor x minus 1 raised to the n minus k, which is 0 at x equal to 1. For k less than n. Therefore, the entire sum reduces to the single surviving term. So this is equal to n factorial times 2 to the n. So we have the part explanation from Taylor series. So step by step, we start with the f of x equal to x minus 1 raised to the n times x plus 1 raised to the n. So substitute here t equal to x minus 1. So x is equal to t plus 1. So the x plus 1 here is equal to 2 plus t. So we substitution here. So f of x equal to f x equal to if x is equal to 1 plus t. So we have t to the n plus 2 plus t to the n here. Now 2 plus t to the n can be expanded using the binomial theorem. All right, this is the binomial theorem in terms of 2 plus t to the n. And multiplied by t to the n here. So we have the product here. So note here, note carefully, when k equals to 0 in the sum, the term is t to the n here, k equal to 0. So 2 to the n, so we have the 2 to the n here, because n combination of n taken 0 at a time is equal to 1. So 1 times 2 to the 2n equal to 1. So we have here 2 to the n times t to the n. So the coefficient of 2 to the n is equal to, and f of t is equal to 2 to the n. So indeed, it occurs only when k equal to 0 in the expansions above. So relating to derivatives at x equal to 1, t equal to 0 here. So if we expand f as a power series in t, so a sub 0 plus a sub 1t plus e2 t to the power plus in general we have e sub n plus t sub n and so on. Then the coefficient of e sub n here equal to 2 to the n. So for zero series around x equal to 1, t equal to x minus 1. So we have f of x. So m derivative of f at x equal to 1 here over m factorial x minus 1 raised to the m. So this is equal to the summation of a sub m to the m. We have a sub n. A sub n here is n derivative of f of 1 here over n factorial. Therefore, this term is equal to 2 to the n. So by multiplications, so multiply both sides by n factorial. So in derivative of f of 1, and derivative of f at x equal to 1 is equal to n factorial times 2 to the n. So we have a conclusion here. This shows that the derivative of f of x evaluated at x equal to 1 is n factorial times 2 to the n. Because in the stereo expansion in t, the coefficient of t to the n is exactly 2 to the n. So it is a neat simplification due to the substitution t equal to x minus 1. So we have the final result here. So with Rodrigues formula. So substitute the c sub in here. So we have the uh, p of x here, pn of x here is equal to 1 over to the n factorial times the n derivative of x squared minus 1 of raised to the n. So we have the interpretation here. So the polynomial x squared minus 1 raised to the n is in accordance to the boundary conditions. The boundary condition here is x squared is equal to positive 1. So that is negative or positive or negative 1. So differentiating n times reduces degree to n. So the normalization ensures Pn of 1 is equal to 1. So orthogonality naturally by integration by parts. So we have the explanation here. So step-by-step explanation of the results. So the polynomial x squared minus 1 raised to the n encodes a boundary condition here. So we have the factor here x squared minus 1 to the n. So we have the factor x minus 1 to the n, x plus 1. So this has 0 of order n at x equal to 1 and x equal to negative 1. So this ensures that when differentiating n times, the resulting polynomial x will satisfy certain properties at x equal to 1 and negative 1. So which is important for solving boundary value problems. For example, in physics, like Laplace equation, spherical coordinates. So in Legendre original problem, gravitational potential, these points corresponds to the Paul's angle equal to 0, and pi here is spherical coordinates. So differentiating n times reduces degree to n. So this is the interpretations. The expression x squared minus 1 raised to the n has degree to n here. So taking n derivative reduces its degree by n. So Pn of x equal to has degree n. So we have example here. So if n equal to 2 here, x squared minus 1 raised to the 2 is equal to x to the 4 minus 2x squared plus 1. We have a degree 4. So differentiating twice here, we have 12x squared minus 4. So we have degree 2. So matches n here. Matches. So the normalization ensures Pn of 1 is equal to 1. So the factor this 1 over 2 to the n times n factorial is chosen so that the P of 1 equal to 1. A conventional normalization for Legendre polynomials. So from earlier reasoning, we have the product here of the we have the we factoring x squared minus 1 raised to the n. Here we have x minus 1 multiplied by x plus 1 here. So our t here is equal to x minus 1. So and at x equal to 1, so t here equal to 0. So we expand here this binomial x plus 1 raised to the n. So this is equal to 2 plus t by substituting here. X in terms of t here is equal to x plus 1 in terms of t is equal to plus 1 raised to the n. And multiply by x minus 1 raised to the n. So we have 2 to the n. So the t to the n term in the expansions comes from 2 to the n times 2 to the n. So this is the coefficient of t to the n here. So when we differentiate n times and evaluate at x equal to 1, it turns out the coefficient is 2 to the n in factorial. So dividing by 2 to the n in factorial gives 1. So orthogonality follows naturally by integration by parts here. So we have the orthogonality. So if m is not equal to n, so this is equal to 0 here. So integrations from -1 to +1. So this orthogonality can be proven using Rodrigues formula, integration by parts in times, or m times, leveraging that x squared minus 1 raised to the n vanishes at x equal to 1 or -1 after fewer than n derivatives. You have the rough sketches of rough idea. So let m is less than n, less than n. So write the Pm of x as some derivatives of x squared minus 1m. So integration by parts here, times the transfer derivative onto x squared minus 1n, which still has the factor x squared minus 1 remaining after fewer than n derivatives. But eventually, when m is less than n, after m plus 1 derivatives on x squared minus 1 raised to the n, you still have x squared minus 1 factor. So evaluating at x equal to 1 or -1 gives 0 here.